I think you joined the class for the first time. I never saw you in the class. Is it so? Okay. So I am SRIPAN and I am working as a PMRF research fellow at ITBHU and conducting this live sessions for this course Fluid Dynamics for Astrophysics once in a week for 2 hours is one of the deliverables towards the PMRF scheme. So today this is the 6th week of the live sessions for this particular course, and as we start with some hydrodynamics, we move on to different like subsonic, supersonic flows, and then we find out that for supersonic flows there can be some discontinuity in the form of shock, and then right now we are in a position to find out what is the outcome of having a formation of shock. So that means if there is any shock in the medium, what are the properties of the medium will change and how it will be changed. So that is our point of interest for today's live interactive session. So I will basically discuss a few questions, few MCQ questions, or few more questions on discussion basis, which will enrich your thought process to think about different MCQs given to you for solving them. So yeah, so let me have the slide. So today's first question is, so we have given four options and we need to find out the correct one or correct options. So let us read first the options and try to understand whether that can be correct or not. So what happens is a shock results when the forward and backward characteristics cross each other. So this is just a normal phenomena for, let's say, subsonic speed, right? So forward and backward characteristics can cross each other. That does not imply that there is some discontinuity. So it cannot be the correct option. It cannot be, because this is not the reason behind the shock formation. Now the second question is the shock results when two forward characteristics or two backward characteristics intersect. Yes, it's true, because then at some point of time you will have some double valued function or double valued parameters, and which is not possible mathematically, and then it gives rise to some discontinuity which can be shock. So the second option is correct. Then you have the term involving grad square u, that is the second order derivative of the flow velocity in the Navier-Stokes equation, is negligible near the shock. Fourth one is similar, but it is saying that it is very important near the shock. Now as we know that when there is a shock front, what happens is there will be some shocked gas and unshocked gas across the shock, which will have different velocity. So that means there is a difference in the velocity in that small length scale. Now if we go to the second order derivative, we are having a important value of grad square u, which we cannot neglect, right? So for this question, this third option is not at all correct. Fourth one is obviously correct, because grad square U is actually very important near the shock, and that means your viscous term is very much important when you are considering the when you are considering the scenario in the vicinity of the shock front itself. So the answers for this question should be 2 and 4, and yeah, so I hope it's understandable to Bimal. Kindly respond.
Yes, sir.
Yeah, it's fine, right?
Yeah, it's fine.
Okay, thank you. So the second question is here. Consider a shock formed in an ideal gas of some finite temperature T. So what will happen if the temperature of the gas increases sufficiently? It is to be noted that the speed of the gas flow remains unchanged. Now first of all, we need to recall again that when shock can be formed. Shock formed when there is a supersonic flow. Now what do you mean by supersonic flow is, you have some flow velocity, you have local sound speed. So flow velocity, let us denote the flow velocity by let's say the flow velocity is V and your sound speed is Cs, right? Now for supersonic speed or supersonic flow, what will happen is this V has to be greater than Cs, right? Now the question is suggesting that this V is unchanged, that means V is constant, right? V is constant, you have Cs. Now as you know that the sound speed Cs, it is proportional to root over temperature, right? So V is remaining constant. Now as you increase the temperature sufficiently, it will increase the local sound speed, right? So at some point of time it can happen that this V becomes less than Cs, because Cs is kept on increasing as you increasing the temperature. So in that regime, or in that condition, so you will have a transfer from supersonic to subsonic, and you should not have the shock. So what will happen is the shock will disappear after a certain amount of increase in the temperature. Okay, so yeah, flow velocity being constant, then flow velocity being constant as T is increasing, sound speed will increase, there will be a condition when V will become less than sound speed, and hence shock will disappear, right? Okay, fine. Now the next question is, choose the correct options. So in reality, shock front thickness will be much lesser than the mean free path of the gas particles. So first of all, what do we mean by mean free path? Is you have a gas container in which so much particles are there, and those particles are collisional particles. That means it can have some particle-particle interaction. So in between two successive collision, how much distance it will cover without any collision, right? That is given by the mean free path. That is what is defined as mean free path, right? So now the shock front thickness. Now, as we know, when you start to think about the shock, we tell that there is just a infinite discontinuity, right? That means there is no thickness. Thickness is considered to be zero. But in reality, shock front has some thickness, right? And as you can remember from the discussion have in the class, that this delta is basically this nu is the viscosity by u, right? U being the velocity. Okay. Now what happens is, if you consider this nu, so nu has some microscopic description, right? And the microscopic description is like nu is centimeter square second inverse. That means it has some length scale associated with it, as well as some velocity. And the velocity in this case is the mean particle speed, which is the sound speed itself. And u here, since we are talking about supersonic speed, so u can be the 2-3 times, or 2-3 times of the sound speed. So that means order of the sound speed. So considering these things, you can find out that delta is of the order of lambda, right? Where lambda is the mean free path. So delta can be higher than lambda, right? Sorry, will be much lesser than mean free path. That is not the case. You can have some lesser fact like lambda by 3-4, depending upon the Mach number, because u can be greater than Cs, but it cannot be very much greater than Cs, right? So for mild supersonic flows, the delta can be comparable to the lambda, not very much less than lambda. Okay, so the first option is not correct. Second one is, with the increment in t, thickness of shock front remains same. Now the fact is, you know the lambda, right? Lambda is the mean free path. Now what happens is, if you are increasing the temperature, what will happen? It cannot be, lambda is proportional to t. As you increase the temperature, so what happens is, you have more thermal energy in the system. So you have collision, but you have the increment in the lambda itself. Okay, so as lambda is increasing, so your thickness of the shock front should increase with the increment in t. So basically, lambda is proportional to some temperature via some functionality. So this cannot be a correct answer. This is not correct. This is not correct. Now the third one is, with the decrement in t, thickness of shock front will increase. Now as you see, now t is decreasing, so lambda will also decrease. The thickness of shock front should decrease, not increase. So it is not also the correct answer. So we are left with this none of the above. Okay, so this is the thing. So insert, so this would be the correct answer. Okay, now so is 4. Now coming back to our next question, that we have some mathematics here. So what we have is, consider the following 3D wave equation. So you have a wave equation which is three dimensional. That means it can have x, y, z if you are considering the Cartesian, or it can have r, theta, phi if you consider the spherical polar coordinate. Now you see that, assume this system to be spherically symmetric. So what does it mean by spherically symmetric? That if you are changing theta and phi, it cannot have any influence on the value of f. Okay, so that means grad square f only depends on the radial component r, right? Now in spherically symmetric system, or in general more spherically polar coordinate, so you could have the grad square f as yeah, pin. So you can have grad square f. There are two more terms, but for spherically symmetric it is sufficient to take this one by r square del r square del f del r, right? Now you have grad square f equals to 1 by r square del r square del f del r, and now one has to plug right. So also consider another equation which can be computed from the wave equation, right? Now you need to find out the relation between g and f. So what you can do is, you have this equation, you can plug the value of f as g, and then you can find out whether you are finding this equation, right? So you have c squared, right, sorry, del 2f del t square equals to c squared del 2f. Del 2f means you have 1 by r square, then del r del f del r. Okay, now you can put 1 by 1 this one, or otherwise what you can do is, you can think of it that how should you do, right? So for example, if we put f rt equals to r g rt, that means you have the r is this del 2 g by del t2, because r is not a function of t itself. So you have c square by r square, you have del r, right, and you have a r square. Now f is r gr, right? So you can have two terms here. One is for just you have g plus you have r del g del r, right? Now moving on to this, it can have c square by r square, right, del r of r square g. That means you could have 2r g plus r square del g del r, right, plus you have del g del r plus, sorry, you could have extremely sorry. So r squared g can have two terms, r squared this, you have r cube there, so you could have r cube means second, yeah. So as you write this one, so you can have r cube means 3 r square, right? Plus you could have r cube, then del 2g del r square, right? Now in any case, this should not give you this formula, right? Because you have del g del r term and also 2rg term, and it should not be the case, okay? So what I am going to do here is, the first one is not correct. Now if we do for the next one, which can be, the next one is like g by r. So instead of putting this, you have let's say 1 by r, right, del 2g del t2, right, equals to what, c square, right? So there is a c square, so c square by r square ddr of r square. Now we have del r of g by r. So you have 1 by r del g del r, right, minus, right, yes, minus g by r square, okay? Now if we look at this, is c square by r square, you have del r, and then you have r del g del r minus g, right? So c square by r square, now del r of this, so this should be, del g del r, right, plus r del 2g del r2 minus del g del r, right? So this one and this one should cancel out, and you will have the c square by r square, r here, so it can have c square by r, right, del 2g del r square, right? Now consider this two, 1 by r can be cancelled out, so del 2g del t square equals to c square by del 2g del r, right? So this one is the correct answer, okay? Fine. Okay, so insert the text box, okay? This one is the correct answer, okay? So symbol is there, fine. Now the next question is, consider air and hydrogen gas. Now the flows in air as well as hydrogen gas is supersonic, so shocks will form. Now comment about shock thicknesses within air and hydrogen gas. So as I was discussing just before the calculation, or in the in a previous question, so the shock thickness, this delta, is nu by u, right? Now nu is the viscosity, okay? Now we have air as well as hydrogen. Now among air and hydrogen, air is more viscous than the hydrogen gas, okay? So what happens is, nu and here we are not bothered about the u. So we are only considering the new vector, and new at ear is greater than new at edge 2. Okay, so if it is the case, now how can we comment on the shock thickness? That is, as the viscosity term is higher for the ear, it can have the more shock. The shock form within the ear will have a higher thickness than that in the hydrogen gas. Okay, so that means delta AIR, which is shock thickness, will be greater than delta in H2. Okay, so this is the case. Now, okay, let me take some time to write the answer here. Yeah, so shock thickness is proportional to viscosity of the medium, since here is more viscous than hydrogen. Shock thickness in air medium will be that in okay, so this will be your answer for this question. Okay, now the next question is, in plasma, in solar atmosphere, there are frequent particle-particle interactions, making it collisional plasma, having smaller mean p path. Now, when you have a collisional plasma, that means you have a smaller mean p path, and the shock thickness will be of the order of your mean p path. Now, but in solar wind, although particle-particle interactions are less frequent, so if the particle-particle interaction is less frequent, what we are thinking that then solar wind cannot be modeled or cannot be think of in the fluid description, because when you are thinking about the fluid description, you are neglecting those small scale details of each individual particle, because those particles are very much in collision with each other, right? So the main free path is very much smaller than the entire length scale under consideration. So we can think of it as a fluid description, that is a bulk flow instead of individual particles motion. Now when we have the solar wind, the particle-particle interaction is very less frequent. There is a rough estimate which tells that you have from sun to earth, you have 1 AU distance, and within this 1 AU distance, that is approximately of the order of 10 to the power 8 kilometers, or yeah, something like that. So if it is the case, then the protons within the solar wind on average can have 3 collisions. So 3 is just a finite number, it is not infinite, right? It is not very much high, so we cannot think that it is a collisional plasma in the solar wind. Now if we cannot think like in the fluid description, because the number of collision is very much less, then how can the fluid description can match with the observation? So there must be some catch which we don't consider right now. So see, you can have particle-particle interaction, but you can also have some turbulence center, right? some scattering center, and your proton, instead of interacting with another proton, it can interact with the other scattering centers, right? And when you are considering the mean free path, you are considering the effective mean free path, not the mean free path due to only particle-particle interaction, but you are considering the mean free path, which can be effectively considered uh, keeping in mind all the details of different types of interactions, right? So you have a particle-particle interaction or proton-proton interaction is very much less frequent in solar wind, but still you can have a very frequent particle, that means proton, and different scattering centers due to some turbulence in the solar wind. You can have very frequent collision in between them or interaction in between them. That leads to very small effective mean free path. Okay, so as your mean free path is very much smaller, then you can consider the fluid description. Okay, so this is the case. Okay, so if we try to write the answer for this, see, answer by mean free path, we are concerned about effective mean free path instead of that arising due to only particle interaction. Okay, fine. Now due to only particle interaction in solar wind, proton interactions may not be much frequent, but there can be frequent collisions between protons and different scattering centers as a result of turbulence in solar wind. So effective mean path is small enough to neglect the motion of the particle and describe the solar wind dynamics by application of fluid description. Okay, so this will be your answer. Fine. Now coming to the next question. Second, it can have much better view. Yeah, so that's it. Now So here consider a shock within a monatomic gas having flow velocity of 5 times local sound speed in the shocked region. Similarly, consider a shock within a diatomic gas having flow velocity of 4 times local sound speed in the shocked region. Estimate the ratio between density ahead of the shock and behind the shock in both these cases. So hint is the density jump condition. So what happens is, let's say I have a let's say I have a shock front going like this. So again, drawing is not that good. So let's say you have a shock front going. You have some medium behind the shock, you have medium ahead of shock, and this is the flow of the shock. Okay, so you can have this is ahead, okay, and this is behind, right? This is also termed as upstream and downstream. This is upstream and this is downstream. Now why this is so? So if you were a lab observer, you are saying that okay, shock is moving in this direction, flow is also moving in this direction, but let's say an observer is sitting on the shock front itself. So what it will see is this ahead flows are coming towards the shock. That is the downstream for him, because it is he is seeing that the flow is coming towards him. So this is downstream, and in this way he will find out that the flow is going behind him. That means he will see the upstream. Okay, so now if you remember the density jump condition, so this is the density jump condition can be written as, that means let's say this is the 1 denoted by 1, this is 2. Okay, so density jump condition is like rho 1 by rho 2 equals to gamma minus 1, gamma plus 1, and then 1 by m square 2 by gamma plus 1, right? So this is 2 by gamma plus 1. Now what is the same? M is the Mach number in this 1th region, right? So that means M is P1 by CS. CS means the speed in the sound speed in this region. So this is the Mach number which we are considering. So it is telling that the shock region means what is behind the shock, because shock is already propagated through that region, right? So this is the shocked region, shocked. Okay, now what we have is, you have a monatomic gas, let's say case 1, right? You have a rho 1 by rho 2. So you have a monatomic gas, that means gamma is 5 by 3 minus 1 by 5 by 3 plus 1, okay, plus 1 by, now AM is basically P1 by CS1, so this is 5 times, so this would be 5 square, something like that, and then 2 gamma is this 5 by 3 plus 1, right? So this will be the ratio, and now ahead of this is your so just the inverse of this, right? So you could have 5 by 3 minus 1 is 2 by 8, so this is 1 by 4 plus 1 by 25, 8 by 3, so this is 6 by 8, which means 3 by 4, right? So you could have 1 by 4 common, and then 28 by 25, that is 7 by 25, right? But you are interested in row 2 by row 1 because row 2 is the ahead, so this is basically 25 by 7. Fine. So this is the first case for monoatomic gas. Now the same way you can find out the other one for diatomic gas. What you need to do is for monatomic, okay, this is the case, right? So okay, so what I need to do is just yeah, so just a second. So similarly what you can do is let me have a new slide. So gonna have rho 1 by rho 2. Again for the diatomic gas you have gamma minus 1. Now for diatomic this is 7 by 5 minus 1 by 7 by 5 plus 1, right? And then you have 1 by that, this time this is 4 times, so this is 16, and this should be 2 by 7 by 5 plus 1. Okay, so this will be 2 and this will be 6, sorry 12, so 1 by 6 plus 1 by 8, right? This will be 5 by 12. Okay, so you can find out the result using this one. Okay, now okay, let's move on to the next question. So you have, suppose a gas is flowing, just a second, yeah, so suppose a gas is flowing at a speed 5 times the local sound speed, forming a shock. So what it tells is your Mach number, this M, is basically 5. Okay, now the flow is then accelerated somehow to 10 times. Now you have a M1 which is 5 and you have a M2 which is 10. Okay, now initially the downstream density and the pressure are 4 times than those of upstream motions, right? So initially what happens is that you have rho 1 which is 4 times rho 2 and you have pressure P1 equals to 4 times P2, right? Now you can remember that when M is greater than 4, okay, we can consider that M is greater than 1. Okay, now in that case what happens is the rho 1 by rho 2, that will have the normal formula for this is gamma minus 1 by gamma plus 1, as I write in the previous question, 1 by m square and then 2 gamma plus 1, right? So now if m is greater than 1, this should be 0, right? So gamma minus 1 by gamma plus 1. Now you see, for m greater than 1, you don't have the dependence on Mach number in the ratio of these densities. Now if the density, as it is already 5 which is greater than 4, so it is greater than 1, so you don't need to consider the Mach number here. So rho 1 by rho 2 will remain same. But for pressure, what we'll have, for the pressure in the limit of m greater than 1, the pressures are defined as gamma plus 1 by 2 gamma square by m square, right? Now what you can do is, so in initial stages, so basically this ratio P1 by P2 is depending on 1 by m square, right? Now let's say I have defined this P1 by P2 by del P, okay, equals to P1 by P2. Now in the initial stage you have this delta P at 1 in the initial stage and delta P at 2. This should be equals to m2 by m1, right, and its square. Fine. Now you have m2 is 10, m1 is 5, so you have this is just 4, right? So del P1 will be, del P2 is this, so you know the delta you know the this one, so which is del P1 is just P1 by P2 is 4, so this should be 4 by 4, which is just 1, right? So that means your P1 and P2, this will be same in this case. So there is no discontinuity in the pressure, you see? Yeah, according to calculation, this is your answer. Okay. Now the next question is, before moving into the next question, give me just 1 2 seconds. Okay. So choose the correct options. So a fluid flowing, so give me just a few seconds here, cut it, and then so we have a new slide, insert image, present, could have this one. I think this is fine. Here it should be here. Okay, this one could have a new slide, insert, so okay, now moving on to this question. So choose the correct options. So a fluid flowing with velocity 0.5 times local sound speed, that means you have a subsonic flow, to start with. When you have 0.5, that means you have a 0.5, and then you have super sonic, right, which is 5. That means you have the Mach number is less than 1. In this case Mach number is greater than 1. Okay, so what will happen is there is two things. So fluid is flowing through some pipe, so what will happen is there's a mass conservation, which is rho a u should be constant, and if you go to the differential form of this, you will get some equation. And also considering this fluid to be in viscid, from the momentum conservation equation, what you find out is you have two equation, right? Rho p dot del v, this is equals to minus grad of p. Okay, so now if we just consider the one-dimensional flow, so what we have is rho v del x plus del p del x equals to 0. Another thing will be coming from here, but differentiation of this. Okay, and also you need to consider another thing is Cs square should be, so this is basically this is equals to so this should be del p by del rho. Okay, so using this formulas you will find out an formula like m square minus 1 by u, right, du dx equals to 1 by a. A is the cross sectional area of the pipe, dA dx. Okay, so this is the case, this is the formula we are looking for. Now when you have the subsonic flow, that means m is less than 1, so m square minus 1 is negative, right? And also now while entering in a converging nozzle person, that means you have this kind of a thing, right? So this is converging, so as it is converging, so that means dA, your dA dx, that should be less than 0, right? And your m square minus 1, that is also less than 0, as you are considering the converging flow, sorry, as you are considering the subsonic flow. Now if you have the subsonic flow and you have dA dx is less than 0, this is also less than 0, so what we have is this du dx should be a positive quantity. That means you have u1 here, you have u2 here, so u2 should be greater than u1 provided your x is in this direction. So that means it will be accelerated, not decelerated. Now we can find out for 0.5 another thing, that a fluid flowing with velocity 0.5 times local sound speed will accelerate while entering in a diverging diffuser portion. Now instead of this one, if you have a diverging diffuser, that means dA dx should be greater than 0, and you have this one negative, so du dx should also be negative. That means it will decelerate. So this one should not be correct answer, this one not be correct answer, you are left with 2 and 4. So instead of 5, second, Okay, so this one the case, and yeah, so this is the case, and then you can remove everything here. Okay, you can just remove and so yeah, so what we have is this equation, that m square minus 1, right? With this you have 1 by u du dx equals to 1 by a dA dx. Okay, so now for 5 times you would have the m greater than 0, so that means, sorry, m greater than 1, that means m square minus 1 should be greater than 0. Now for converging, what will happen? For, let's say, the second one, they will have dA dx, that should be less than 0, right? So if it is less than 0 and this is greater than 0, that means you will have du dx that will be less than 0, right? That means decelerate, right? So you can see that a fluid flowing with velocity 5 times local sound speed will decelerate, right, while entering in a converging nozzle portion. So this is the correct answer. Now the last one is, again, now we have a diverging diffuser portion. So what will happen? So diverging diffuser portion, you will have dA dx will be greater than 0, and this is also greater than 0. So what will happen? Du dx will be greater than 0, right? So this is acceleration, ACCL, right? So this one has to be a correct answer. Okay, so fine. Okay, now the next question is, for an ideal normal shock, the normal component. So first of all, what is normal is you have flow velocity as well as the shock propagation velocity, right? Shock propagation direction. So if the flow velocity and the normal to the shock both are in the same direction or parallel or perpendicular, that means it is normal shock. But when you have the shock propagation direction in a some different angle with the flow velocity, that means it is a oblique shock. But in this question we have the normal shock. So we have 4 options. So first one is the normal component of velocity is continuous across the shock. Not at all, because as shock is propagating, you have shocked region, unshocked region, and in the shocked region the velocity will be decreasing, right? And that means there is some discontinuity in the normal component of velocity. But so the first one is not correct, this one is obviously not correct. The tangential component of velocity is discontinuous across the shock. That is not the case, because as shock is moving, only thing which is discontinuous about the velocity is the normal component, not the tangential component. So tangential component remains the continuous. So this is not also the case. The shock heating is a manifestation of transition from supersonic to subsonic flow. So what happens is, you need to understand one thing, that across the shock you will have this half u square plus total internal energy, let's say half u1 w1 equals to half u2 square plus w2, right? Now let's say this u2 is the shocked region. So what will happen is u1 will be greater than u2. That means w2 should be greater than w1. W2 is basically nothing but the internal energy, which depends upon temperature, right? So if internal energy has to increase, that means temperature is also increasing, and that can be done by the shock heating, right? Because due to the heating, the temperature is increasing, and as the temperature is increasing, your internal energy is increasing as a manifestation of the conservation of the total energy within the system or within the flow, right? So this one is correct. Now for an ideal diatomic gas, which will have, first of all, this is not 5/3. This should be, gamma has to be 7/5 here, right? This should be 5/3. So the density jump across the shock can have a value of 7. So how can I tell that? So basically, you see, the M value, this can have the value of greater than 4. Now the density is like rho 1 by rho 2, that should have the value of gamma minus 1 by gamma plus 1, right? So if it is the case, or the vice versa, let's say this one rho 2 by rho 1, which is the case, this gamma plus 1 by gamma minus 1. Now for this one, for diatomic gas, you have 7/5 plus 5. 7/5 plus 5 is 12, and you can have gamma minus 1, which is 7/5 minus 1, that is 2, which is equals to 6. So this is the maximum value it can have, because you have 1 by m square. Now you have, if m has some value which is greater than 1, that means it can give you some extra value, right? And so this is the maximum value which it can achieve. So it cannot have a value of 7. Okay, if you remember that plot, you can find out that as Mach number is increasing up to a certain extent, like say m greater than 4, you can have plateau, right? It should not have any rise or decay kind of structure in the density ratios. So that means the density ratio is fixed for higher values, and the higher value of the density ratio can be at most 6, not greater than this. Okay, so this is not also the case. So okay, fine. So let me take it and let me have a new slide. So the next one is choose the correct options. So transition from supersonic flow to subsonic flow can be only due to formation of discontinuity like shocks. So first of all, let us remember what shock does. Shock can change a supersonic flow to the subsonic flow, but not the vice versa. So supersonic flow can change to subsonic flow via shock. But whether it can be done only due to shock? No. There is a nozzle like this one which has some diverging as well as converging system, right? It can give, this is a reversible thing which is known as D Laval Nozzle, right? D Laval Nozzle. And so what happens is, this is a reversible process. Why? Because let's say you have a supersonic flow going in. Okay, now if supersonic flow is going in, what happens is, here you have M which is 1, right? So here you see dA dx is 0. Fine. So when it reaches here, it will reach less velocity, right? Now then it is having a diverging thing ahead of it. So dA dx is greater than 1, right? So it is starting on supersonic. It has some decrement in its velocity as it moving forward, because it will decelerate here. Then it can go to the subsonic regime, and as it is goes to subsonic regime, so you have m less than 1 here. Why? It has lesser velocity, it becomes mild subsonic, and then the diverging cross section is there. So dA dx is greater than 0. You have m which is less than 1, so that is m square minus 1 is less than 0. That means you have that du dx should be less than 0, right? So that means you can have lesser velocity as you go to the x-axis or x direction. So start with supersonic and then go to subsonic, okay, due to the D level nozzle. Also there can be another criteria, that you start with subsonic instead of supersonic. So if instead of supersonic you start with m minus 1, m is less than 1, so what it does is, it will accelerate here, so it will go to the supersonic regime. Now the supersonic flow, you have m square minus 1 greater than 0, you have dA dx which is greater than 0, right? So you have du dx also has to be greater than 0. So what does that mean is m greater than 1. So for D level nozzle, you can have a transition from supersonic to subsonic, subsonic to supersonic, okay? And shock can only do the transition from supersonic to subsonic, not the other way. So can be only due to formation of discontinuity like shock. This is not correct. Transition from supersonic flow to subsonic flow can be without formation of discontinuity like shocks. Now what you are trying to do is supersonic flow to subsonic flow without formation of discontinuity like shock. As I said, yes, it can happen. Transition for subsonic can be without formation of discontinuity like shocks. This can happen. Now transition can be only in the presence of discontinuity like shocks. Now no, as subsonic cannot be changed to supersonic by discontinuity like shock, so it should not be a correct answer. Okay, fine. So what? Yeah, so that's all for today. I don't know whether Bimal is already there or not. Bimal, are you there? So you understand everything? Okay. Okay. So if you understand everything, then it's fine. Uh, so I will stop here for today. This is the end of content for today's interactive session. We'll meet on next Saturday for the 7th week live interaction session. So thank you, Hemal, for attending this session. I hope others will join in upcoming sessions. So thanks one again. You can leave now. Bye bye.